Good morning, everybody. For me, it's a complete honor to be here at NDC stage. I have learned a lot from these conferences, and now here I am at this stage, together with such brilliant people sharing my thoughts. It's a complete honor. Thank you very much for making these events possible. I'm going to beg you a couple of questions. How many of you know what TDD is all about? Whoa, it's much more than I was expecting to be. Yeah, great. And how many of you are practicing it daily at your work? Much less? Okay, that was the proportion that I was expecting to find. But you know what? These two questions are wrong, because they are aiming into a possible solution that we could end adopting, but not on the real problem that we are trying to fix. So let's try to reformulate the questions. How much time does it take since we have an idea till it's finally working in our product? How many changes have we made since the last complete test run? Do we find difficulties to comprehensively test whether those ideas work as expected in our product, as well as our previous ones keep working as they were? Do we need any kind of debug on hardware in order to do that? These are more proper questions, right? And you know what? I know firsthand that the differences out there are really huge. They range from several hundreds of lines, lasting days or even weeks, while having to deal with different types of hardware, till a single line of code in less than a minute by only using our development environment. And the differences are not strictly indirectly related with the essential complexity of the products that we are building, but on the accidental complexity that our development processes prevents us to combat mercilessly. Back in 2009, something happened that changed my professional career. We were developing fully electronically controlled small wind turbines, and I was in charge on the embedded software control. It was a disruptive concept, and we had several orders already waiting in the queue. We had a small wind tunnel in our facilities in which we were able to put the small wind turbine to work and test most of its dynamics, but not all of them. For example, the cases where it was facing strong gusts of wind. We had been working really hard to have a final release ready, because in 2 weeks, a strong wind storm was arriving to our test facilities. And you know, we need to have everything ready to face the wind. 2 days before the D-Day, my manager came to my desk and asked me a totally fair question. It was like, Fran, is it going to work, right? And you know, fair question need to be answered with honesty. I said, yes, I hope it will. Hope? He cut me off mid-sentence. It looks like you don't have control about what you're doing. And he was right. Even having done my best, I was completely unsure. In fact, I had nothing in my hand beyond code reviewing and hope. I guess you know what happened when the windstorm arrived. The wind turbine entered into an improper control loop, due to a bug, for sure. It accelerated beyond its nominal speed, and it broke down in pieces. My code happened to be mere dust in the wind. It was a lucky event, however, because during the next months, I have a recurrent nightmare in which this event was happening in a wind turbine installed in a schoolyard. You don't have control about what you're doing. Those words keep resonating in my head during the next coming years, like a splinter in my head. But how on earth could I have managed to test those corner cases, to execute those paths, without having to have the full system working and facing these strong gusts of wind? Looking for answers to these questions, nearly by accident, some years later, in 2016, I got aware of the TDD existence of TDD. And the funny thing is that neither my colleagues nor my technical managers have heard about a word about it. Nowadays, it's a more spread technique, or at least it's an acronym that is more well known, but I still deeply believe that that is a completely underrated technique in most development environments, and in embedded, even more. My goal today is to try to live up to the challenge, to show you some of its main benefits in action, and you will judge if I have accomplished my goal. So, but before starting, let me make a little introduction about me and my current context. Let's see if it works. have tried before. Okay, let's do it in that way. My name is Fran Climent. I am a telecommunication engineer with major in electronics. I have been, well, I started working as hardware engineer back in 2007, but soon I moved to software and firmware. I currently work as senior R&D software developer at Kongsberg Discovery, Spain. At Kongsberg Discovery, we create state-of-the-art maritime solutions and systems, like the ones you can see in this slide. And Kongsberg has several facilities in my country, but our main headquarters are located in La Vila Joyosa, which happens, it's a small and beautiful city, coastal city, close to Alicante, which happens to be my hometown. We are currently 18 engineers there, working ensemble among different teams around the globe. Apart from that, as technical coach, I usually help teams and organizations to improve their development processes. Probably most of you know that Kongsberg is a great company to work for. We have the proper Kata and really good technical challenges. We are continually looking for talented team players. So I invite you to join, to visit this webpage and take a look at the open opportunities that we have around the globe. So, but why another talk about TDD, right? Which is the motivation? In this talk that I delivered in the past, I presented the major impediments I have found so far in the embedded development realm, as well as some of the solutions that I have used trying to eliminate or reduce those roadblocks. This talk can be seen as its practical companion. Here I will try to show you some of the movements, some of the design decisions that we could do, that we could face when we are following in the real action. So, without further ado, let's start. And let's start by trying to get feedback from the hardware. The approaches that we usually follow by an easy example. How would we assure the coders really turn on and off an LED? Easy, right? Easy question. Common approaches that I have found to these questions lay in one of these categories, like measuring the voltage, measuring the current loop, using a logic analyzer, or even using some kind of external photo detector. And all these approaches have something in common. They tend to put hardware into all our software development loop. And for sure, we are embedded developers, right? And for sure, we will need to use the hardware in some moment. But I deeply believe that we might rethink when do we want to let it into our development processes. And here is where the meta-lean development approach comes to the arena. Its main goal is to make possible to create and evolve any embedded code, much faster and safer, iteratively and incrementally. Good, right? How are we going to achieve this? Key thing, always, right? Continually looking for ways to get feedback faster. That is going to be the key cornerstone for us. And in order to achieve this, we will need to treat as much embedded code as possible as an independent subsystem. Let me try to explain what I mean with that. None of the previous approaches give us any proper feedback about how our code is really behaving. Short circuits, open circuits, fuse loads, bad soldering, all of them have a real impact in the voltage, electrons, and photons involved. But none of them have anything to do with how our embedded code behaves. So, in order to do the previous step possible, we will try, whenever possible, we will try to use really cheap software in the loop, known as test doubles, instead of hardware, instead of any hardware in the loop. Because there's something that is really key here, is that absolutely nothing happens in the real world if it doesn't change a special function register bit. Nothing, even those strong gusts of wind. And if we take this into account, we could try to put our embedded code into a matrix, right? We are going to fake it that the external events are happening. How? Using test doubles that will interact with the special function register that we need at our convenience, whenever we want. We will also rule the time. And yeah, which is the outcome? For sure, we will need to, yeah, we will do a better code, better software, right? Better architecture. Yeah, this is again, is a low-level detail. What it really matters is the business outcome. What we are going to achieve is to have an increased embedded development in lead time at a sustainable pace. So we will be able to give the customer value, to provide to the customer value faster and safer. As most of you probably have guessed, we are going to follow an evolutive design and development. And specifically, we are going to embrace this one, the one that acknowledges our limitations and divides the development in 3 strategical steps. It's named at make it work, make it right, and make it fast. During the make it right, we are focused in trying to understand how to solve the problem, not about engineering the code right. During the make it right phase, we will be trying to engineer and craft the code right in order to make it easier to understand, maintain, and evolve. And these 2 differentiated stages should exist because barely no human being is able to do both things properly at the same time. And last but not least, make it fast, right? We're embedded developers, fast enough. Let's try to fulfill the system timing requirements if we have, but take this into account that this is one of the common traps in the embedded realm, is that we follow in the global performance pre-optimization trap. We go directly to the 3rd step, which makes us even harder to reach the first one, and almost impossible to go to the 2nd one. So the best implementation I know so far for this evolutive design and development is by following TDD. If we follow its 3 differentiated stages, red-green-refactor, we will be transitioning among these 3 differentiated stages several times per minute, as we will see in the example in a few minutes. And Meta-Lean test-driven development encompasses the well-known dual-target TDD approach, as stated in James Gleaning's book. We will be running our solution and our test for sure, both in the final target environment as well as in our development environment, also known as the host. At least from the very beginning, we will be running in 2 different platforms. Maybe they are going to be portable, or maybe not. We will see. What Meta-Lean emphasizes is to treat as many units of behavior from metal to metal. What means is from microcontroller inputs till microcontroller outputs. Units of behavior. And in some cases, it will be enough to run till stages 1, stages 2, stage 3, only by running on our development environment, as we will see in the example. But in other cases, we will, for example, when we are aiming or talking with an external integrated circuit, we will need to go to the stage 4 and stage 5. Just run it into the real hardware, right? In order to validate whether our understanding of the datasheets are correct or not. So when I was looking for an example in order to show you the technical practice in action, I knew that it should be something that it shouldn't be a toy, right? Something that it will be able to reproduce the kind of decisions that one could face in the real work. But at the same time, I didn't want it to be complex, because the goal of the example is not going to be to solve a complex problem. It's going to be to show how we can solve it, right? So what could be better than use this or kind of hello world, right? Blinking LEDs. And this is the Kata. This is the example. I call it the 4-level battery monitor. I choose a bare metal, 8-bit bare metal microcontroller in C. I choose a really constrained environment in order to show that even in those constrained environments, these things are possible. This is the current hardware variant that we are going to use, right? We are going to have 4 LEDs connecting to the port A high nibble. And yeah, that example belongs to a bigger workshop that I have created that lasts almost half a day. So I have to try to synthesize as much as I can. And one thing that we are not going to see is from the inputs, I mean, from the sensing the battery, right, through the control, this part is not going to be seen. We are going to see only the other part, the outgoing part, the driving the LEDs. We are going to pretend that this is going to be the first internal usage of this microcontroller in the company. So we don't have any kind of processor abstraction layer. I will explain what that means later at all. It's brand new for us. And for the reason of time, as I said, we are going to pretend that the battery status percentage provider module is being developed by another team. So we are going to use a test double for it. The goal, the goal is to develop a highly decoupled and portable battery monitor module. If you have faced the semiconductors shortage, but if you have it, there are certain, for example, there are certain development environments where they have finally understood that the web or the databases are simply I/O devices. They are not core centric to our architecture. So maybe we should rethink that a microcontroller is simply a running detail. Should it be centric? So we should be able to change it with little to no effort. So let's do it. Before starting, this is going to be the development environment that we are going to use, simply because it's the fastest embedded environment, the fastest environment I have found for this kind of embedded C. If I am continuously looking for ways to have something that goes even faster. This is the key thing, right? We are going to use Seedling. Seedling is a lightweighted unit testing framework for C. It's really tiny, so it's able to be loaded into even in tiny microcontrollers. One additional feature that is really good for the Seedling is its automated test double creation. It's a really nice feature. For the IDE, we are going to use C-Lion, mainly because of the state-of-the-art automated refactorings. Unfortunately, I have not found any vendor-specific tool that aims into that direction, and this is going to be key for us. And the tool chain, I have chosen GCC, but you can use Clang or whatever. It really doesn't matter. Well, this is for vendor agnostic. When we talk about the current vendor, because current, we should be able to change it. It's going to be Microchip. In this case, we are going to use its cross compiler, and something that is really nice and important, we are going to use its simulator. Microchip provides a simulator that supports almost all its microcontrollers. And a simulator should be something that we should ask the vendors to provide. These are really nice tools to have. So, yeah, let's try to start. Let's try by trying to understand those written in stone specifications. Well, even though the stone is made of silicon. This is our beloved datasheets, right? So you remember we have the LEDs connected to the port A. If we go to the microcontroller's datasheet, we will see that in order to command to high a given GPIO in the port A, we will need to write into the port A bit 7, for example, if we want to write this bit. Setting this bit to high will mean that we will put a high level in the GPIO. Setting a 0 will mean that we are putting a 0 in the GPIO. Additionally, if we want to read the value in the GPIO, the datasheet state is that reading from the same port will give us the actual IO pin value. Nice, awesome, we have everything. So let's start. Here you have the framework in action. This is the test suite that I have created. You can see that here I have created some helper functions. We have it, assertion functions, some helpers. Here we have the common setup and teardown that are present in almost any XUnit framework. And each of these functions or methods are an independent test. I have tried to follow the given when then approach in order to explain what they do. And we have several of them, and each of them is covering a specific corner case following the boundary value analysis testing technique. So they define, each of these values define the points where an interval of behavior starts and ends. That means a partition. So, yeah, some people say, okay, that's nice because you knew which were the tests you need to have. Even if you don't know, well, even if you don't know by advance which test do you want to do, this is nothing that is going to prevent you to use TDD. Because when you write a line, you know what you are doing, at least. Let's put a test for that, right? So let's start. Let's start by running the framework in the target for the very first time, taking into account how much time does it take to run. I will explain later what happened behind the curtains. One thing that I want to mention is that all tests are currently ignored, right? If everything is right regarding the framework itself, it should pass. Everything should be green. So, yeah, here we have it, right? 27 seconds, not bad, right? Let's see what happened under the curtains. What Silly did was creating the test runner for us, cross-compiling it using the cross-compiler. It did the same with the test suite itself, using the cross-compiler. And later it linked everything together, creating the binary executable that is able to be flashed into the microcontroller. But you know, we don't have a microcontroller. We have a simulator. And what it does is, in order to run it, it uses the simulator. It loads the test runner into it. This test runner is going to write into using the output char through a UART, and the output of this UART is derived to a common text file. And this is the text file that we are going to retrieve at the end. Here you can see these are the results that are written by the microcontroller through the UART and recovered from the text file. And as you can see, the format is a well, it lasts 8.6 seconds to run of the 27, and the format is a GTest format. This is why C-Lion is able to understand what's going on behind the curtains. So let's go for the first specification. Yeah, the one that says that at 0% of battery, all LEDs should be off. Easy. So the first thing that we need to do is to enter into the red state. Okay, and here you can see in the assertion, you can see that I have used a mask in which I have put, this F is because we are only focusing in the high level, and we are asserting that is 0, right? The high level should be 0 in order to pass. So if we write that thing, if we activate all of the GPIOs, this test should fail. Let's see it. Let's run the test in the target. I have it speeded up, right? Not 27 seconds. Whoa! It passes. Totally unexpected, right? That means that we are not being able to put these GPIOs too high. Maybe, yeah, but your friend, you know what? I need to see it in the hardware. I need to see it in the lights. See lights, right? So let's flash this running into the target and see that effectively they are off. Let's do that. Here is flashing the test running into the final product. You can see the rhythm. This is the rhythm we are used to have. As long as we put hardware into a loop, it gets slower and slower and harder to reproduce. You know as well as me. Okay, it's flashing it. Let's see, now it's flashing. Yeah, they are off, effectively. We have been unable to command them to on. And this is because, for sure, there's something on the written in silicon stone data sheet that we haven't understood correctly. So let's take a closer look to the datasheet, and we will find that there are a couple of additional special function registers involved in that stuff, and they are the trees A and unseal A. After reset, all these values are 1. That means that by default, all GPIOs on the port A in this microcontroller go to analog inputs. That's the thing. We are not able to command it because they are analog inputs. So let's configure, in order to do it, to configure them as digital output, we will need to write a 0 in the corresponding trees A bit, which means that we will be, the output driver is enabled, and also writing a low level into the unseal A corresponding bit. That means that the input buffers are enabled. The combined effect is that this digital output, this GPIO, is going to be configured as a digital output. Let's see. if we have correctly understood what should be done. Let's do that. Let's configure the port A to have all of them as digital outputs. Let's run the tests. And yeah, it's failing. It's failing by the reason that we were expecting to fail. That means that we have correctly activated the GPIOs, the LEDs. Okay, you don't believe me. Let's see it in the real hardware. Let's flash the test runner now. The test runner in the final product, and they are on. Awesome. So we are finally into the red state, right? Now it's time to make it work as fast as possible, right? Here, our common under engineering is really welcome. We can do whatever we want. We can be complete sinners here. Let's do it really ugly, right? Let's do it. Oh, which is the minimum implementation to make this test pass? Yeah, this is the minimum thing. Let's do it. Let's do it here directly. Yeah, all to 0. It should pass. Let's see. Oh yeah, it does. We did it. Oh, all of them are off now. Okay, again, most of you probably need to see it in the real hardware. Let's do it again. Sorry. Sorry, it's going to be repeated. Let's see it in the real hardware now. Let's flash the runner into the final product and see that effectively they are all off. This is going to be the very last time that we are going to run it into the hardware. And in fact, I have been using it only because I know we are so used to seeing blinking lights in order to believe, right? No more tests into the loop. Okay, nice. We are in green. Awesome. Now it's time to make it right. Now it's time to refactor. Now is where we will engage a little bit more brain cells, right? A little bit, not too much. Let's try. That is the moment that we will try to put in all our business logic, right? Put it in means that let's keep it away from the low-level details. This is the thing that is done here. So you will agree that this line shouldn't be there. It belongs to production code, right? So let's move it to a proper method using the IDE refactoring tools. Start method, and we are calling battery monitor update status. Okay, create it. You can see the definition and the implementation is there. We are running the tests. We should be green. Yes, they are. Yeah, now we can move it to this proper module. Next step. Let's move it there using the IDE refactoring tools. We are going to create the battery monitor module, the one that we need to be working on. Setting that we want this method to be there. Move it, yes, create it. Yeah, it has been created inside the test folder. Sorry for that. We are going to move it to the proper source code. There, I have moved it to the entities source code folder. Great. Just open this source file and the header file by a moment. And let's run the test again. It should be green, right? We are refactoring. And they are. We are green. Awesome. Perfect. Look at these include files. They belong to the testing framework. And they shouldn't be there. Well, I don't know why the IDE has done. But they should not be needed. So we should not include anything that we don't depend on. And this is one of the little things that we start to take a closer look when we start doing later baby steps. So let's remove these header files. And let's mark, by the same reason, that this include is there, this one, the battery monitor is there because this source file is implementing its API. Let's put it there. It's there because it's implementing this. Okay, let's run the test. Fine, passes. Awesome. Great. Let's see now the same microcycle, red-green-refactor in a complete run. Let's go for the next spec. Okay. Here it is. The net spec is the one that says that 24%, all the status LED should be off. So let's put the proper arrangement phase, copy paste. Ooh. Let's copy paste it, right? We are setting the port A to digital outputs and setting the desired output as the complement, all high, because we are expected to have all of them low. Let's run the test suite again. We should be red. And yes, we are by the expected reason. Okay, we are in red. Minimum implementation to make this test pass. What about do the same? Let's put it to low unconditionally, right? So let's call the production code the same way it is, and it should pass. Let's see. Yeah, it passes. Awesome. Fake it till you make it, right? So time to refactor. These 3 lines are duplicated. And even these 2 are really low-level details that we have correctly understood maybe a few minutes ago, but for sure we are going to forget it in the near future. What do these 2 lines mean? They mean that, yes, so let's put this information that we have in our mind into a proper method, right? Extract method, and it's given the port A, GPIOs are all outputs. Easy. Okay, let's run the test again. Yeah, it passes. Awesome. Let's move the definition to the end of the file. We don't want to have it in the middle of the tests, low-level dates at the bottom. Okay, let's remove the duplication using it in the other test. Run the test again. Yeah, passes. Awesome. What about this sentence? It's also a really low-level detail. Do you remember why we put it there? Yes, it means given that the port A high level are all on. Same. Run the test again. Passes. Awesome. Passes. Move it to the back of the file. And let's mark this section is a custom givens section. And let's use it in the other test, removing the duplication. Not rocket science. Run the tests, and it passes. Okay, fine. It's a little bit better. Let's take a closer look to our dependencies. We have 2 modules, the battery monitor, this is production code, and the test suite, the test battery monitor. Both are using a SIM in order to, it's called processor selection.h, in order to incorporate the microcontroller package when we are running on target. And there are some arrows that crosses an architectural boundary. It's the hardware boundary. These are marked in red. These arrows are there because we are using the port A and ANSI A and trace A, are the ones that make these modules firmware. They are firmware because they depend on something that is hard to change, right? What is hard to change? Our running microcontroller, okay? So yeah, we could try to address this thing now, but I'm not going to do it. I'm going to wait a little bit more and put more behavior in place before doing it. And you could ask, why? You know what? We are following TDD, and we are the ones who drive. In this case, it was me. I decided to do it in that way. It's the only reason. Okay, so let's go for the next one. The next one is the one that states that at 25%, only LED 4 should be on. Let's put the proper arrangement in order to enter into the red. In that case, we should, the binary complement of the expected output is E0, is E in the high level. And let's call the production code. It should fail. We should be in red. And it fails. It fails because LED 4 is not on, right? Just the thing that we were expecting to have. And now we cannot fake it anymore. This test is going to force us to finally ask for the battery percentage. So we are, as I said, we are going to use this module that the battery change status provided, get charge percentage, and we are included. Yeah, it's include the header file there. We are going to mark that this include is there because this is a collaborator. We are using it. And if we run now the test, we are still in red. But we are in red because the build is broken. And it's broken for sure because we don't have any definition or implementation for this method. It's the one that we were pretending that is being developed by another team. So we are going to use a test double for it. In the way in which it's done with CMOC and seedling is by making an include with the same name of the API that we are pretending to mock, but with the mock word in front of it. If we run the test now, we will see that the build works. So it has created the test double for us, but it's failing. Not only the test that we are working on, but the previous one that we're passing now are red, failing. And the reason is because we are calling this method more times than expected. This is because seedling by default uses strict mocks, right? And you know, mocks tend to know too much. Right? They are really appealing, really easy to use, but be aware that they know too much. Anyways, we are going to use it, but we are going to hide it in a few moments, right? So let's try to put the other one, the previous one that we're passing into the red state again. What is missing is the expectation, right? Let's go to the one that is at 0 battery percentage level. The way in which the expectation is set up with CMOC is by calling the same method or function, if you want to be pure, followed by expect and return, and passing the desired value. Right? If we do this and run the test again, the test suite, we will see that this test is passing again. Okay, fine. Let's fix the one that is at 24. This is this corresponding expectation. Fine, passing. This is the only one that is missing, right? The one that we were working on. Let's put its proper expectation. It should be that the battery is at 25. And let's run it. Yeah, it fails. And now it's failing by the reason that we were expecting to fail, because LED 4 is not on. We are in red, finally. So minimum implementation to make this test pass. I think that you will agree that the minimum thing that we could do is to do this thing. If the battery percentage is 25, deactivate the LED 4, else let's clear them all. Yeah, awesome. It will pass. Yeah, it does. Green, perfect. If we have a battery with 0, 25, we are done. Okay, time to refactor. Do we have anything else? Maybe not, but okay. It's time to refactor. So, you know what? This line here knows too much. It knows that we use a given, a battery change status provided, a given module, a specific module to retrieve the battery. It knows that we are not using its production code, but a test double instead of that. And it also knows that we are using a mock test double. And additionally, it knows that we are using CMOC for it. Too much, right? I have had to explain the meaning to you a couple of minutes ago. So let's hide it behind the proper sim. That is going to be a proper sim for the future. We are not going to see it in the example, but this line means given the battery charge status is, right? And we will set it here the desired battery percentage. Yep, we could pass the battery percentage, extract the method. Okay, here we have it. We should pick the input parameter and pass it to the mock framework. And with that, we should be done. Let's run the test again. And we should be green. Oh, Jesus! No, now it's red. What the hell? Whatever it is some lines ahead, maybe a couple of lines ahead of this, right? Okay, let's check what I did. Okay, I pass a 0 here instead of 25. Okay, let's fix it. Now it should be passing. And it does. Awesome. Let's move it to the back of the file, to the end of the file. And this is going to be a custom arrangements section. Here we have hidden this low-level detail. Let's use this proper arrangement method. Well, let's run the test again because we have moved it to the end of the file. Fine, we are done. Let's use this give a proper method, arrangement method in the other ones, 24, and in the one that is at 0. We are running the test all the time in the background. So 0, fine. It should be passing. Ah, yeah, it does. Fine, a little bit cleaner. So these are our current dependencies. Now you can see that both the production code and the test code, and the test code depend on the new collaborator, this provider, and you can see how the test suite has instantiated the test double for it. You can see that the hard to change dependencies are still there. The horror is, we will fix it later. So let's go. Well, before that, you have seen that it lasts 27 seconds to run, right? It looks like it's really short, but in reality it isn't. Once you start practicing pair programming or team programming, and you need faster feedback, you will realize that it's really annoying. So this is one of the reasons why we are going to try to run it in the host, and also because if we are able to run it in the host, it's going to be portable, or maybe not, but at least we will have additional tools like are available in plain C, the tool chain, right? So let's try to do that. So let's run it in the host. As I mentioned to you, we are using GCC for this endeavor. And for sure, it's failing, right? It's failing, yeah, you can see we are using GCC. Here we have done the same, it has created a runner, compile everything and run it, but for sure, it doesn't know what the port A is. Obviously, we are not incorporating any microcontroller package, right? So how could we fix this thing? One way to do it is to apply the separation of concerns. Because one thing is assuring which values are read from or written to a specific memory address, and another complete thing is whether this memory address is exactly the one that is where the special function register is, right? So let's take advantage of this, and as long as the framework activates this flag, it's the test host, whenever it runs in the host, we could create really cheap fakes for it, right? When we are running the host. If we run now, well, yeah, for sure we need to access from the test suite. Let's create the global variables for it, and let's run the test now. Now it's building and it's running in the host. We are registering the time. Yeah, 10 seconds, almost a third of the one that it took on the target. We are getting better. Apart from that, as I mentioned, as long as we are using a plain C tool chain, we will have plenty of new tools. We are no longer constrained to be embedded, right? One of the tools that we have is the code coverage. As you can see, we are running now with code coverage, but we will have any kind of sanitizers, rule checkers, you name it, mutation testing, for example, you name it. We have, yeah, that's what we have. So back to our dependencies. Our code is portable, isn't it? It's running 2 different platforms. Well, no, not really, because even though it's running the host, it's instantiating these ugly globals variables. Bear with me. It's going to be something momentarily. We will fix it. But not only that, because this belongs to a specific microcontroller. Not only that, we are also putting some code that is there only by testing purposes in our production code. That this is an smell. It shouldn't be there. And yeah, sometimes when we refactor, we take some steps that worsen our code in order to be able to take bigger steps or faster steps in the near future. That's the thing, right? So let's continue. Let's continue by adding some behavior. Let's go for the next corner case, is the 49. So let's put the proper arrangement. Now, yeah, it's the same thing. Iterative status, it should be failing because let4 is not on. We are in red. Time to make it fast as possible, right? And here we are going to employ a technique that allows us to have, with briefly in time, a duplication between production code and test code. It's named triangulation. What triangulation means is like this 25 that we have there and the 49 that we are now dealing with define an interval of behavior, right? So we know there's going to be a less or equal or greater or equal in some way, right? But we will wait a little bit to have this generalization in place till we have more corner cases covered. So let's fake it a little bit using the triangulation. Easy. So if the battery percentage is 25 or it's 49, let's activate the LED 4. Enough. It passes. Let's do the same with the 50. Let's go for the 50. At 50% now, LED 4 and LED 5 should be on. And now the binary complement in the high level is C in hexadecimal. Let's call the production code, run the tests. And yeah, it fails just by the reason that we were expected to fail. LED 4 and LED 5 are not on. Minimum implementation to make this test pass. You will agree that it will be enough doing this thing. If the battery percentage is equal to 50, let's activate LED 5 and LED 5 and LED 4. Let's run the tests. And it fails. Why it's failing? Do you have any clue? Yeah, I forgot. I missed it. Yeah, defect localization. So yeah, I forgot to activate LED 5. Let's do it. So now we should be passing. We are done. So now we are going continuously with this triangulation stuff till we have all the corner cases covered, running the test suite all along the path, right? All along the process, till we have all of them in place. So we have it. We have almost the 100. Here it is. Okay, fine.
You can see TDD is really fast.
Yeah, when it's it looks like this, yeah. But yeah, it is. It could be. So now it's time to refactor. Well, before refactoring, we forgot to run it in the target. It's going to be working the target. Let's run it in the target. It should be working. We haven't done anything strange. Who knows? 2 different platforms. Yeah, it passes. Okay. Time to refactor. Now is where we could put this generalization in place. Let's do it slowly, right? So yeah, for sure, if the battery is bigger than 25 or less than 49, LED 4 should be on. So let's do this thing. And if we commit any error in the process, it will point it out, like it has been done. Okay. And yeah, we can even revert the order in which we are doing this thing. Let's try that. Let's see if it passes. And yeah, it does. And you know, this is last if statement is redundant. We can remove it. Yeah, it is. And look at this. Yeah, these are also redundant. We can remove them. Much cleaner. Yeah, fine. Now is where we are going to finally address the issue, right? Let's try to make our code independent of the microcontroller. This is the production code that we currently have. As you can see, there is a single statement for each of the intervals. Forget by a moment the low level. we have been putting to 0 all the time, right? Skip it by the moment. Take a look at the high level. We are dealing with it's 4 bits at once, because it was the easier way to do it, because in our current hardware variant, we were using these 4 GPIOs on the port A. But you will agree with me that it's impossible to say, okay, hardware colleagues, you are not able to use any GPIO. You should go to this one. So this can be moved, right? So one thing that we will need to do is to deal with each of these bits independently. Because if we do that, we could also put a proper abstraction in place that will be able to deal with each of these individual GPIOs. But in the way the code is, in this shape, this is going to be hard to do. So one thing that we are going to do is first make the change easy, right? We are going to try to put everything in place to make the easy change later. So we are going to these sentences, we are going to try to put it as the equivalent, but with the sentences that are dealing with each individual bit individually. These are the common masks that we are used to use when we are in embedded, right? Dealing with special function registers. One after a time, right? And yeah, you can see they are equivalent. So now, let's run it in the target. Don't forget that. And yeah, it passes in both. Awesome. Now we are in a much better shape to finally make the easy change. Let's call it easy. We'll see. As you can see here, we have 2 types of sentences. One that clears a given GPIO, and the other one that sets the GPIO to high and the other to low. This sentence over here means setting to low level the 4-bit in the port A. What we want now is to extract it to a method that is going to be called PAL under GPIO low. PAL comes from processor abstraction layer. Its goal is to hide which microcontroller are we dealing with. And we will need to pass something in order to know which GPIO do we want to address, right? And here is where we need to put all our brain cells in action, because whatever we put there that unveils which microcontroller is behind the coroutines will counteract its original intent. When that happens, we call these abstractions leaky abstractions. And unfortunately, most hardware abstraction layers from the vendors happen to be leaky abstractions. So take this into account. So let's use the IDE and create a PAL GPIO low. What about passing a uint 8? What about that? If we do that, we will be able to address 256 independent GPIOs. Maybe it's more than enough. And one thing that we do that is that the port, this port thing, it goes away. It's a low-level detail, right? So let's do that. Here we have it. Let's run the tests. And let's move each of these corner cases or implementations to this behavior. And probably some of you are not thinking, yeah, this is a really switch case if-else statement. We should be doing some shifting to the left and masking. You're right, but not now, not yet, right? Not yet. So let's do the same with the PAL GPIO high, and let's start removing, yeah, it is the PAL GPIO high, and let's start using it and moving all the code through this method, each by each, right? It's always faster to let it work in that trying to fix when it's broken. Fine. Let's run it in the target, right? It should work. And it works. Great. This PAL GPIO method should not belong to our module, right? They should be to the proper module. So let's move it there. Let's create a PAL GPIO module. And let's mark that we want both methods there. Just create it, yeah, do it. There, here we have. Yes, we have it. Let's see. This is the source file. Ooh, here we have some include that shouldn't be there, like before. But we will remove it in a moment. Let's remove them. It's no longer needed. And let's mark specifically that this include is there because this source file is the one, the only one that is implementing this PAL GPIO for this microcontroller. Right? Great. Run the test again, and it fails. Totally unexpected. And it fails because I have been unable, because it's not finding the PAL GPIO high. And this is because I have been unable to make seedling deep dependencies to properly work, and it's not compiling the PAL GPIO. So if we put this sentence over here, we will force the framework to compile it. Now it's compiled, but yeah, you see, port A is undeclared. Okay, sure, it isn't. We are running the host, right? What if we? Okay, let's make it pass fast. What about? Let's copy these globals here and use it there. It should pass. Yeah, it does. Awesome. We are closer. We are getting closer. But the battery monitor module is these lines, the lines 10 to 12, are the ones that are making this module firmware. We don't want it to be there, right? So let's move these lines into the proper PAL GPIO. And let's run the test again. It should pass. Hey, awesome. It doesn't know anything about which microcontroller is under the coordinates we are using. The only thing that is missing is to moving this PAL GPIO here file and source file to the proper folders. So let's do that. The source file, the API, is going to be in the PAL interfaces folder, and the PAL GPIO is going to be inside this concrete microcontroller implementation. And let's run the test again. It should be passing. Let's run it by the very last time in the target. And it passes. We're done. Finished. Okay, closer look to our dependencies now. As you can see, the production code is no longer dependent on anything, it's not crossing any hardware boundary. So it's independent on the microcontroller that we are using because we have inverted the dependency using this abstraction. Unfortunately, we have been unable to do the same with the test suite, which is really unfortunate because it should be done. We do have plenty of time to do it. But you can see these globals are still there, but at least they are only in the implementation for the specific microcontroller. It's better. And when we run it into the target, we don't have these ugly things, right? These fakes. We are incorporating the microcontroller package, and we are done. So I showed you, okay, incompleteness before you yell at me. I haven't showed this method, right? Because for sure we should be able to set which GPIOs do we want to use for each status LED. Sure, it should be. This kind of init should be there. And additionally, you will be all the time maybe thinking that this is an ugly thing, right? Really naive, and you will be thinking some variant of the one that you have here, right? So masking and shift and left shifting. Right, agree. But this thing, in order to transition from that one to this one, we will need to test drive it using its proper test, right? In order to cover all the corner cases, even the low level that we have been pretending that is zero all the time. So yeah, this is the end. This has been my little contribution to a practical technique that allowed me to start playing to win, like Ken Beck explains in his book, Stream Programming Explained. Obviously, we will never be the one like Neo in the Matrix movies. But however, we really deserve better development approaches to gracefully fly while facing shifty winds of change, right? It's time to fly. Thanks for joining me. No, I don't know if we have time to any questions. Maybe yes.